Good morning. Good morning to all of you.
Good
Good
morning,
morning,
sir.
sir.
Okay.
Good morning,
Good
sir.
morning,
Good
sir.
morning, sir.
Good
Good
morning.
morning, sir.
Good morning, sir.
Hope you are all keeping fine. And today we'll discuss another important reactions and its kinetics, that is competing reactions. Right. So that I'll present you. And after that, if we get time, then we'll discuss the reversible reaction. One example of that. And okay, so let us first start with these reactions of competitive nature that I'll present first. Okay, okay, okay. So competing first order reactions, right? Competing first order reactions, or sometimes it is called parallel reaction or side reactions. These reactions are popularly also known as the side reaction, or sometimes it is called side reactions, or sometimes they're called parallel reactions. Okay. So what is the kinetics of that? Uh, so for this we have considered it. So examples in the right hand side it is given. Look, say uh, this is the electrophilic substitution reactions in phenol, and say electrophile E plus, if we put, then it can be either ortho, because which is ortho and para directing groups or activating groups. So naturally you will expect the two products, say if we label it reactions, reactant A. So reactant A is the phenol, and this phenol, so this is the reactant here A. It reacts with an electrophile E plus, whatever, it may be nitration or like any other kind of electrophilic reactions, electrophilic substitution reactions, as you know, that which is orthopara directing group. So you get two isomeric products. One is ortho product, we label it as D, right? This is labeled as D, and another is para product. Here we label as, say, suppose C. Whatever you can say, this is C and D, doesn't matter. And with the rate constant K1 and K2. So both the steps, that is whether A to C or formation of A to D, both obeys first order kinetics. This is very important. Both the reactions, side reactions, or competing reactions, that is A to C or A to D, they represent uh, the, they follow the first order kinetics. Okay. Now, suppose if we write down the overall rate of formation of A, rate of formation, or you can say rate of accumulation of A. So that would be equal to minus, because A has been consumed in both steps, so naturally negative signs would be there, and we can write minus K1A minus K2A. K1A means the rate of consumption of A in the first step, and the rate of consumption of A in the second step, that is K2A minus K2. Okay. And this can be rearranged like this, minus K1 plus K2 into A. Now let A equal, if you integrate this equation, just like it seems to be a first order reactions, right? Normal, you know that what is the differential rate law and what is the corresponding integrated rate equation, that you know. So that's why we have written like this. And can we write like this? A equal to A0 into to the power minus K1 plus K2t, because here, here, this is a constant quantity, rate constant, and it is taken as K effective. We can put K effective. So now, what is the concentration of C and what is the concentration of D? That we have to find out. Okay. So A equal to this expressions, and what is the rate of formation of C? Can we write like this? Because C is formed only in the first step, which is equal to K1A. Since it is formed, so the sign is positive naturally, and we can put the expression of A from the previous expression, and it becomes simply K1 into A0 into e to the power minus K1 plus K2t. Okay. Now this equation again can be rearranged in this form, that is dc equal to this. And if you integrate within this time, that is from your start time at the start of the reaction, that is t equal to 0 is taken normally to any finite time t. And when at t equal to 0, naturally, there is no formation of product. So concentration of C in the lower limit should be equal to 0, and that at any time t, let the concentration be denoted as concentration C, as in the integral sign in the left hand side, you see. So these are the limits of the boundary of the integrations. Okay. And if you integrate, so we can write concentration of C, because C minus C0 is 0. So C equal to C K1A, which is constant, K1 is 0. You can take it outside of the integral sign, and it will be simply like this, e to the power minus. And it is very straightforward to integrate within this limit. If you put, right, then what you get? You get an explicit expression of C, that is equal to minus K1 is 0 by K1 plus K2 into e to the power minus K1 plus K2 into T, minus, if you put T equal to 0, naturally it will be equal to 1. So this is a very simple and straightforward expressions where we can find the product concentration in terms of the, as a function of T, okay, time. And this equation can also be written in alternative form, in this form. That is, if you just absorb the negative sign, then the uh, expression in the parenthesis will be changed like this. That is 1 minus a to the power K1 plus K2 into T. So this is the expression, final expression of the concentration of C. That is one of the isomeric product. Now what happens? If you follow the similar algebra to find the concentration of the other isomeric product, that is D, right? So it is a simple exercise that you can easily find that K2 into A0 by K1 plus K2 into 1 minus e to the power minus K1 plus K2 into T. Okay. So right now, what we have done, we have, starting from the differential equation and assuming that these side reactions both obey the first order kinetics, based on these assumptions, and we ultimately uh, find that explicit expression of the concentration of both the products, isomeric products, how these varies with time, that explicit expressions we find. Okay, and it is very interesting to see that the constant quantity that appears before the parenthesis uh, is almost similar, right? Since product C is formed in the first step, so you can easily remember that the rate constants that appear in the numerator is K1 and that of T, that rate constant, because D is formed uh, in the second step, not second step, in the parallel reactions, that is K2, rate constant K2. So in the numerator, you can find the rate constant K2. Okay. So other quantity, that is the factor, that is A0 by K1 plus K2 remain constant. Okay. Now at any time, what we can do, because there are two rate constants, K1 and K2, and you can, if you put a ratio of this, if you want to find the ratio of the two products, that is C and D, what is the ratio of these two concentration of the two products at any time, then what we can write? Can we write it in this form, K1 by K2? Yes, because you see the factors, only K1 and K2 refers, other things remain constant. Even identical, not constant, identical in the right hand side expressions. If you look at the expression of C and D, so only quantity is that differs the K1 and K2. So we can find this expression, that is the ratio of the concentration of the product C and D is given by this equation. And another equation that we can construct, that is the overall rate constant, simply K or K effective, whatever you can write. Here it is K, that is equal to K1 plus K2. Okay, so this can be measured experimentally following the first order kinetics. As in the first order kinetics, one can easily determine from experiment uh, that that is, if you plot concentration versus time, there are several ways, that if you know at least two times different measurements at two times the concentration of product, then one can find using this data the value of the rate constants, right? So this K overall rate constant can be measured experimentally following the first order kinetics. So right now, you see the two we are interested to find out the individual rate constants. What is the value of K1 and K2? So for that, right now we have two equations or two expressions, right? Because concentration of C and D you can measure at any time during the population of reactions, and from that information you can find out the ratio, what is the value of K1 by K2. Even at the end of the reactions, when equilibrium is attained, right, as if no more changes in the product concentrations are noted. So after a long time, when the reaction appears to be completed means it reaches the equilibrium state virtually. Okay. So in that case, we can also take, we can measure the concentration of the amount of C and the amount of T left in the reaction mixture, and from that ratio we can get actually the value of the ratio of the constants K1 and K2. So by measuring the concentration of the products, isomeric products C and D, you can find one expression like this. So two unknowns K1 and 2 to the equation, so you can easily solve. Okay. Now there is a quantity, there is a terminology that we maybe heard, that thermodynamically controlled or kinetically controlled products. What does it mean? That we will discuss. But before that, we may discuss the nature of the variations of this. Uh, concentration of isomeric product. Okay. Now let K1 is greater than K2. Let K1 equal to twice K2. Sorry. Sorry. Let K1 is equal to twice K2. This is the assumption. Now, if you plot the concentration of reactant A by E0, and it will follow an exponential decay, as in the first order kinetics you see, it appears like this, right? Steeply falls like this. And what about the ratio of that concentration of C by E0? It is given by this plot, middle plot, right? And the lower plot, that is D by is plot concentration of D by. We are plotting versus K. So this is the typical graph. And naturally, this is one assumption that K1 is greater than K2. So that concentration at any time would be formed at a greater extent. If the reverse is case, then G should be higher. Okay. Now, suppose C by D equal to, as if we take K1 equal to twice K2, then this ratio of concentration should be equal to 2, because dc by c by d equal to basically k1 by k2, right? It is k1 by k2, and this is equal to this quantity, and it should be equal to 2, and k1 equal to k1 plus k2. Okay. Now, what is the equilibrium concentrations? Equilibrium concentration means if you take that is the limiting value when T is large, when T tends to, then from that expressions you can see that we label the concentration C. E stands for equilibrium concentration of T, likewise equilibrium concentration of D is denoted by D subscript E, because the exponential factor e to the power minus k1 plus k2 into T, that factor vanishes, right, when T tends to infinity. Because if we allow uh, infinite time, then the reaction will virtually attain the equilibrium state. As if you find that no more changes in the reaction mixture, whether it is the products or reactant amounts, whatever left in the reaction mixture, these cannot change further. So that's why we can take an infinite time approximation. So the limiting value, and for that case, the concentration of C and D, they attain their equilibrium values, which is equal to this. Okay. Now let us see the what is the kinetically controlled product and thermodynamically controlled product. So we can write C equilibrium by concentration of AE equal to K1. This is explicit from here. That is C equilibrium by A equilibrium equal to K1. This K1 is the equilibrium constant for these reactions, right? Uh, what I say that for these reactions, A to C. So normally we should write this equilibrium constant capital K1 is denoted here is equal to K1 by K minus 1. That is inverse. Okay. So this is the expression of the ratio of the equilibrium concentration of the so the here is we call equilibrium constant. So here K1, capital K1 and capital K2, these are equilibrium constants for the respective reactions. So C, A to C, A and C, this is for equilibrium reactions. Let us consider that A to C and C to A is also possible. That means the isomeric products they are allowed to decompose or revert back to the concentrations. Sorry, reactants, which is A. So you can write like this. Okay. And A to D, similarly, we can write K2. So DE by concentration of equilibrium constant K2. This K2 naturally is equal to what? It would be ratio of K2, small K2 by K minus. Okay. So this is the ratio. So this is the ratio. And I think at this stage, so initially we did not allow the reverse reaction, that is isomers to the reactant, C to A or D to A. That products, that transformation was not allowed at the very beginning, right? We have considered it. But right now, while discussing the thermodynamically controlled product and kinetically controlled product, so let the reverse reactions, that is C to A and D to A, are allowed. Okay. And also not only that, the two products C and D, they can also be interconvertible, right? So interconversion between the two isomeric products, that is C and D, that is also allowed. Okay. So that is I'm written. Let us allow infinite time, and the system will reach the equilibrium state. Okay. And K1 and K2 are rate constants, sorry, equilibrium constant, as we discussed earlier. Okay. So that we discussed, and uh, here you see that this ratio of concentration, what is the, if C and D are allowed to be interconvertible, that is reversible, then what is the equilibrium constant? Ce by concentration of dE, the ratio of the equilibrium concentrations. And that we can write like this. We write the product AE in the numerator and denominator. So basically it will be same expressions, but look, sorry, divide. We should divide, not multiply. It is divided like this. Okay. So basically this we can write in this form. The purpose is to identify the numerator that I have written here as equilibrium constant capital K1, and this is the capital K2. Okay. Okay. This is very interesting. Look, now, so that means when this is when you are allowing this reversible, that is A to C and A to D, this implies that the product C and D, they are also interconvertible, and the corresponding expressions you can write like this. And we write here capital K1, that is equilibrium constant for step 1. And step 2 means A to C and A to D. We have written explicitly here. Okay. Now, what is thermodynamically controlled? That is, thermodynamically controlled means which product will be produced ultimately. That means which would be expected to be produced in greater yield, whether isomer C or D, which would be formed or produced at a greater extent at the end of the reaction. And that we call thermodynamically controlled product. Okay. So thermodynamically controlled product means C or D, which will be formed at a greater extent. That is the question. Okay, I'll discuss. Before that, you have any question, please. Okay.
Sir, can you tell me again that how will we determine K minus 2 or K minus 1? Hello, sir, can you hear me?
বাবা, তুমি কি বাইরে তোমাকে বেরোতে হবে? তোমাকে তো বলা হলো বসতে, লোক জিজ্ঞাসা করছে, কোয়েশ্চেন করছে, জানো?
Hello, hello. Can you hear me?
Yes, sir.
Hello.
Yes,
Yes.
sir.
Yes, sir.
Yeah.
Okay, I'll be discussing once again. Actually, initially, see, we have considered reactions C to A to C and A to D, but we didn't allow the reverse step, that is C to A or D to A. Right? That was not allowed at the very beginning. That means we have considered only the forward reactions. But if we allow the backward reactions, that is C to A and D to A, right? C to A and D to A, that is the reverse reactions, if is allowed, then what happens? So that means if whenever we consider the reverse reactions, so naturally there should be an equilibrium, individual equilibriums between reactant A and one of its isomers C, likewise A and D. And for that we have written the explicit expression of equilibrium constant, okay, K1, capital K1 and K2. And naturally, in this case, if you follow the simple algebra, you see concentration of C by D, that would be equal to this. That we can write K1 by K2. And that means C and D, they products, they are also interconvertible. So we are considering in the second phase that, or in the case 2, that reversible reactions as well as the interconversion between the products C and D. If is allowed, then what happens? That I am discussing. Okay. So what is thermodynamically controlled product? Thermodynamic controlled product means what? Normally, whenever a reaction occurs, and if you follow the, if you measure the products which is formed or produced at a greater extent or larger extent, from that you can get the idea, right? Suppose a product is formed, say C or D in greater proportion. That means we say that product, particular product is formed at a greater thermodynamic ease, or it we call thermodynamically controlled product. That we'll discuss here. And as you know, that is which product will be formed at a greater extent, C or D. As you know from the basic thermodynamics, there is a quantity, delta G zero. What is G zero? Do you know what is G in thermodynamics? Do you have any idea?
Standard free energy.
Yes,
Gives
exactly.
energy.
Gibbs free energy, exactly. So Gibbs free energy, G zero superscript stands for, it is
Say at
formed,
equilibrium.
not equilibrium. It is at
Standard.
temperature 298 Kelvin, and a given pressure say 118. So it is a
Standard
standard
condition.
right, standard free energy change. So the whenever a reaction occurs, naturally it is a process. So for this reaction, there will be change in free energy. As the reaction progress, there will be a change in the free energy of the reactions. Now, this free energy change of the reactions means what? Free energy change of a reversible reactions. That is when reactants and products are present in a reaction mixture, then what is the change in the free energy as the reaction gradually progresses? Right? Not necessarily at equilibrium. Whenever a reaction starts, some products are formed, and as soon as products are formed, they naturally have a tendency to produce back the reactants. And as a result of that, we can calculate the free energy change of the reaction mixture. And that free energy change of the reaction mixture, I think that expressions I have not written here, and I think that you know from the basic thermodynamics what is called okay. Gibbs free energy change can be written as an expression reaction quotient. You know, I don't know whether you have that idea. So I can just write simply here, say delta, sorry, I can write say delta G equal to delta G0 uh, plus RT ln Q. Q stands for reaction quotient. Basically, Q is nothing but here Q is equal to basically the ratio of the concentration of C by D. C by D at any time. What is the concentration of C and what is the concentration of D at the same time interval? You take the ratio will give you reaction quotient. So Q is we call reaction quotient. Okay, and we say equilibrium constant K equilibrium that is equal to QE. That means in that case the concentration of C would be equilibrium concentration and D would be an equilibrium concentration. Then the reaction quotient. So basically reaction quotient at equilibrium we call equilibrium constant KEQ. Okay. So here you know a relation exists. I am not going to derive, but it is straightforward. That is at equilibrium, you know, what is the value of delta G? Can you guess?
Zero.
Zero.
Yes. So in that case, can we write delta G0 equal to minus RT ln KQ? Clear?
Yes, sir.
Is it all right?
Yes, sir.
Yes.
Yes, sir.
So that I have written. Here R is the universal gas constant, you know. T is the temperature in Kelvin. Ln log E base, natural logarithm, and K equilibrium. Okay. This is the standard free energy change of the reaction directly related to the equilibrium constant at a given temperature. Okay. So naturally, product will with most negative delta G0 is favored. That I am telling you. Right. Suppose if you compare here, say there are two equilibrium constant, A to C and A to D. So K1 is equal to, we can write this, K2, this expression I have written in this form. Okay. And delta G0 equal to like this, and this is corresponding to this. I have written explicitly, nothing else. And the ratio CE by D equal to what we can write? K1 by K2. And that is equal to the ratio of this. We can write in this form. That is clear to you. E to the power delta G10 minus delta 20 by R. Okay. Now, suppose if delta G10 is much, much less than delta G20, then this ratio implies what? If delta G0 is much, much less than delta 2G0, that means K1 by K2 would be much, much greater than 1, and the concentration of C would be much, much greater than D. So what I am telling you, uh, okay, which product is favored in larger extent? That is the question. So what is the answer? It depends on the relative magnitude of K1 and K2, right? It depends on the relative magnitude of K1 and K2. If K1, here it is, say, rate constant. This is very important. Here, in this discussion, small K1 and small K2, they are basically rate constants. Okay. So if K1 is greater than K2, naturally the product C will be formed at a greater extent, apparently with respect to D. Look, this is the rate of formation. Once again, I'm repeating, this is the rate of formation, right? So rate of formation of C would be naturally greater than D if K1 is greater than K2. Is it clear? This we call, say, formation of C is favored kinetically, or we say kinetically controlled product. So by some means, if we regulate the magnitudes of this K1 and K2, should be one make, if we want to make it higher compared to other. So naturally, we can control which should be the kinetically controlled product, right? Now, at this stage, do you have any confusion? It is very simple. That is rate constant K1 and K2. If rate constant of a reaction is larger, naturally that reaction step would be faster. It is a normal practice and concept normally, usual concept, you know. But what happens? If suppose K1 is less than K2, then naturally concentration of D would be favored. That I have written. Same thing I am repeating for this. Okay. Now, generally what happens? You see, A to C and A to D, K1 and K2 are rate constants. That K1, this is the small rate ratio of the rate constant. This is the ratio of rate constants. Okay, this is the ratio of rate constants. So this is very important. If this ratio of rate constants is much, much greater than unity, that means K1 is much, much larger than K2. And this ratio, that is K1 by K2, capital. So this is the ratio of, equilibrium constant. What is the equilibrium constant? You remember, I think, A to C and C to A, that reaction, that is equilibrium reactions, A, C, and K2 corresponds to the equilibrium constant. So between the reactions A to D or D to A. Okay. So if K1 by K2, K1 is much greater than K2, there you can find that K1 is much, much less than K2. Normally it happens. If the ratio of rate constants follows this order, that is K1 by K2 is much, much greater than unity, the reverse happens. Therefore, the equilibrium constants K1 by K2 much, much less than 1. Now, in that case, what do we say? We say C is favored kinetically while D is favored thermodynamically. Because K2 is larger, capital K2 is larger. So whenever K2 is larger, we say that the corresponding product D will be favored thermodynamically. Now once again, why K1 is greater than K2 and the product will be formed? That follows what? I can show you. in a just simple sketch. Suppose a reaction. Now, if you follow the energy sequence, energy, that is potential energy versus reaction coordinate. Reaction coordinate denotes basically a kind of coordinate, means in terms of bond length like that, so that what is the product, how the product is formed. So if you just trace a curve like this, arbitrary, say A to C, and there is another curve you can construct like this, D. Now look, the height, barrier height, what do you call this barrier height?
Sir,
What is
activation
this?
energy barrier.
Yes. So activation energy barrier of say A to C, and if you look at this curve, which is larger?
D.
So which product will be formed at a greater extent? You just guess. Which should be produced at a larger extent? The product C or D?
C, sir.
C.
Yes, because the barrier height is small. So that means if you follow the Arrhenius equation, what is that? K1 equal to say A1 frequency factor or the exponential factor, we assume A1 into e to the power minus rate constant. Sorry, it would be
Minus
activation
EA by
energy,
RT.
right? Say E1 is activation energy for the first step by RT, and if you follow that K2 rate constant, that is equal to A2 into e to the power minus E2 by RT. So naturally, if the activation energy is smaller, this quantity is negative sign, its magnitude would be larger. So K1 would be formed at a greater extent because the activation energy for this step is smaller, right? So this we call kinetically controlled product. That means by means of any means, if you increase the height or change the height of a reaction, then you can control whether that particular product will be formed at a greater extent or smaller extent, right? If it is a desired product, then you can monitor it by making the barrier height smaller. And if you think that it is not the desired product, or it should be removed from the product, we don't want this product, then naturally we have to control that activation energy barrier. That means we have to increase the height, right? Now there is a question how we can monitor this, because there is only one choice. Can you guess? That is by using suitable catalyst, right? Because catalyst always provides an alternative path with lower activation energy. So this is one way how to regulate or how to control the kinetically controlled product. I think you have some idea here, or any confusion? Hello, can you hear me? Hello,
Yes, sir.
Yes, sir.
is it
Yes,
all
sir.
right? Is it all right?
Yes, sir. Yes, sir.
Yes, sir.
Because if you use a suitable catalyst, then the activation energy barrier normally reduced, right? And as a result of this lowering activation energy, that reaction will be progressed at a greater extent. That means kinetically we can control. The kinetically controlled product means it can be controlled externally, right? But what happened? The thermodynamically controlled product, that you do not know. It depends on the, okay, you can also calculate free energy change of the reactions. That means if you calculate or estimate the equilibrium constant of a reaction, from that you can guess what should be the thermodynamically controlled product or not. Now once again, what happens? Suppose here we assume that K1 by K2, so K1 is much larger than K2 because K1 has the lower activation energy for the step A to C. Now, uh, as we already discussed, but in such a case, C is normally favored kinetically, while D is favored thermodynamically. Why? It is clear from this picture also. Look, if you follow C to A, right? Look, the barrier height will be almost same as my picture drawing. So C to A and A to C, this is reversible and this interconvertible very fast. So that means, but if you follow this A to D, since barrier height is larger, and I'm just as per my drawing, so D to A conversion will also take much time. So that means at any time you can see the population or the concentration of D will be much larger compared to C, right? So that means normally what I've written, if K1 by K2 is much greater than 1, the reverse, that ratio, the equilibrium constant will be reversed. That is K1 by capital K1 by K2 is much less than unity. That is, if C is favored thermodynamically, but D is favored thermodynamically, because D will decompose with less extent, but C will be easily decomposed. So naturally, at a given time, you can find there is a greater accumulation of the product D with respect to that of C. Is it all right? Hello?
Yes, sir, understood.
Okay, okay, thank you. So that I've discussed. So in this way. So I'm not going to discuss anymore because time is over, I think. Yes. So in the next class, we'll discuss the reversible reactions and some chain reactions, or say Lindemann hypothesis and one of its applications. Okay, that we'll discuss in the next class. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Okay. Okay. Thank you.